Yeah, I'm recording as well. So what I was talking about, so in physics there are two problems, there are two parts in solving any problem. First is physics of the question, and second is mathematics related to it. Okay, so if you get the physics right, even if you get the mathematics wrong, doesn't matter, you won't lose full marks. It's not like other subjects. Okay, so you don't have to worry about the mathematics, you just worry about the physics of the questions. Okay, second, in whenever you tackle problem in any field of any subjects of physics, no matter what subjects is, even if it's quantum mechanics, you just have to see what is given in the problem. Every hint trick is hidden in the hint. Okay, that's how you tackle the problem. So when I was in undergrad, I used to think whenever the problem is too complex, like this question in the like this one, or weird shapes, I used to see, oh, integrals involved, too complex, too complex. No, everything is given in the problem. Okay, you just have to see where it is hidden. Just focus on the given part of it. Okay, I'll start with first question. Okay, so before I start, I don't know why it's not showing me your comments. I want to see your comments. I want to see the window. Just to wait another second. Just wait. Yeah, that's better. That's better. Yeah, that's better. And I'll place this here. Okay, perfect. Let's start with the first question. So let's see what's given. So a uniformly charged rod of length L and total charge Q lies along the x-axis as shown. So we have as you see in the diagram here on the right, we have a rod of length L and a total charge Q is distributed symmetrically and uniformly across the length of the rod. Okay, so given so we have given part, charge is distributed uniformly across the rod. Perfect. So what do we get from this charge distributed across the rod? So if I select any length element, let's say dx here, I can find the charge distributed in this. How? The total charge is q, then charge per unit length is q by l, and the charge in this dx is q by l into dx. As simple as that. This is what I got from the given part of it. Now the electric field due to this dx at point P can be written as dE k E dq divided by x square plus d square, where x is the distance. This Sorry, why is it derivative again? No, it's not a derivative. It's the length. So so you divide the rod into small parts dx, and if you integrate dx from 0 to L, you get L. Okay, you divide length into small sub length elements of dx. Okay, it's not a derivative. You got it? Okay, where dq is the charge in the length element x. That's what we found here. We computed there. Okay, now first part says find the components of the electric field at point P on the y-axis, a distance d from the origin. So distance is given as d, and this is as origin. We are asked to find the components, so there are two components, dex and dey. So if you see, if the angle theta is subtended at the point P due to this length element dx that is highlighted here, then dex is nothing but sorry ex is nothing but dx. You sum all over it, you integrate it, and you can sine theta, where sine theta is equal to x by d square plus x square. I hope you got it. So I just theta, subtended theta here. You substitute theta as d by x squared plus L square, and this is x. Yeah. So similarly, you can write ey as dey cos theta, where cos theta equals to d over d squared plus x squared. So it's as simple as that. Now you substitute the values here. So what you get for ex, you have little integrals. I hope you're familiar with integrals. I'm just substituting the values here. Okay. Okay. So I substituted for dq here. I substituted for dq. I substituted for theta, cos theta, and sine theta. And what do I get? I got this. Okay. Now, how do you solve it? It's called integration by substitution. You say d square plus x square sorry, I missed this. There is a root here, 1 by 2, and there is this. So I missed that. Very sorry. You call it integration by substitution. You say d square plus x square is equals to, let's say, u, then 2x dx equals to du. You substitute that here, you get ke q by l du by u. du by u. Okay, and you get the factor of 1 by 2 here. Then you can solve it further. Q by L. Sorry, so somebody's typing. We'll keep solving it. That's what you will get. Okay, I just skipped some steps here. Hope you can do it. If you want me to do it, I can show it to you. And you can put back for u is KEQ by L 1 by d square plus x squared to the power 1 by 2 and the limit 0 to L. So you will get EX as KEQ by L 1 by d square. Can EX equals to KQ by x squared plus d squared? No. Here EX is this. Okay. Here EX is DEX sine theta. So what I did, I have DEA here and I have sine theta here. Okay. And probably this is confusing here. So this is DE sine theta. Similarly is, so I have substituted DE from here and then I substituted sine theta from there and I just put that back into this equation. Does that make sense? Okay, perfect. Maybe the conventions I chose was not fairly. Okay, here we have d square plus L square and I'm just substituting like limits. That's your EX. That's your final answer for EX. And this weird looking thing is Q. Okay. Similarly, you can do for EY. I will write the equation. Okay. Or I'll write it properly. T by square plus d squared to 3 by 2 into dx. Okay, so what you do here, you do substitute x as d tan theta. And if you guys are wondering why I chose this, though it's not a topic of physics, what I'm trying to explain here, or this is not related to electricity and magnetism, but if you see tan theta, then because I substitute x equals to d tan theta, because the problem here, the integral here is 1 by x squared plus d squared. So any integral that is of type 1 by x squared plus d squared, no matter the power of it, is always substituted as x equals to d tan theta. That's one of the tricks in mathematics or in integration, because the integral of 1 over a tan inverse x upon a, 1 over x square minus a square, or x square plus a square, is 1 over a tan inverse x upon a. That's how you get this relation. Okay, we can talk about it if we discuss mathematics. So but if you substitute this, you get the problem. You substitute this integral will simplify considerably, and I did it, so I don't need to do it. If you guys want me, I can show you explicitly, but it is very straightforward. I hope you guys all of you can do it. So this will be the final answer. I'm just writing the final answer. If you want me to show it, you can type, yeah, please show it. If you don't want, you can do it by yourself. This is just the integration. I told you the substitution. Oh, you want me to show it? Okay. I'll show you. I'll skip this answer. Yeah. Okay. So you substitute x as d tan theta. What you get is k q by l d dx by x square, sorry, d square plus d square tan square theta. Also, if x equals to d tan theta, then dx equals to d by cos squared theta. Okay, d theta. Okay, now k q d by l d theta by cos squared theta is your theta symbol for the q. Okay, sorry, yeah, that's my mistake. They look the same. Yeah, you're right. Let me correct it. Okay, they look the same. So I'll type q as qe. Okay, that means, okay, perfect. Okay, and theta is that. I don't know why I'm typing theta as q here. Okay, and this is also theta, not dq. So this is what you get. So if I simplify it further, I get keq by l into d theta 1 plus tan square theta is 1 by cos square theta. If you don't get any step, feel free to type it, okay? You further simplify it to now you have to substitute the limits. How do you do that? So x goes from 0 to l. I didn't type it here. Let me type it. Okay, x goes from 0 to l. So theta goes from, if you substitute it here in this equation, theta goes from 0. If x is 0, theta is 0. And if x is l, theta is tan inverse L by D. These are the limits. So we have limits tan inverse L by D. It's just solving the integral. Okay. Now what is the integral of cos theta? It's the famous old sine theta. Sine theta in the limits. Okay. Now you have to substitute it. Another trigonometric identity is this sine theta, sorry, here, sine of tan inverse x is, can you move the black box? Yes, for sure. Like, I have to read your comments as well. So maybe here for now. Is it okay? Okay, perfect. Yeah, I'll move it. Keep moving it. If I minimize it, then it goes away. Then I have to reshare it back, and then it comes back. Nice. They don't make it user friendly. Anyway, so another identity is that sine of tan inverse x can be written as x by root 1 plus x squared. It's very simple trigonometric identity. I hope you know. If you want me to prove it, I can prove it, but it will just take time. Okay, just look at it up. Look at up in any internet or any mathematics book. All right. Okay. So you substitute it here, and you get your answer back. So you get your answer back by substituting this equation kq by ld. kq. What your equation? This is what I wrote back there. That's your answer for EY. Okay. What wording of this question told you to use this integrals? Whoa. You were not present here? Okay. Here. This says find the component of electric field at the point P. Okay. So at point P, we have two. So electric field at point P has two components, Ex and Ey. I'm just solving Ex and Ey due to the finite element dx, and I'm integrating dx over whole length L. Does that make sense? Hey, can we see the answer for Ey again? Yes, I'll show it to you. And I'm not the one who is setting up your exam questions, okay? And this is okay. Don't fear the mathematics here. That's what I said before. In physics, you have two parts. Figure out the physics of the problem, and then there is this simple or some mathematics left. I won't say it's simple, but some mathematics left. So even if you get the mathematics wrong, if you still get the physics right, if you still get the question till this point and this point, you still get the marks. Okay, so don't fear the mathematics. If you practice it, you'll get the mathematics correct as well. If you have any problem related to integrals or anything, you feel free to send me your questions. Okay, I like mathematics. I don't know why, but yeah. Okay, but so this is our UI. Okay, let's go to the second part of the problem. Second part of the problem is what are the approximate values of the field components when D is very greater than equals to L. So when D is very bigger than L, if you see here for the B part of the problem, B part, if D is very greater than L, if D is very greater than L, then you substitute it there, then Ex can be written as Ke. You can neglect L, e square 1 by 2 minus 1 by t minus 1 by t, which is 0. So ex goes to 0, ex goes to 0, and ey for d very greater than L, we have here, comes out as ey equals to keq by d square. So let's see whether they make sense or not, these results. You don't have to do the mathematics to get these results, okay? Physics will tell you. We got these two, ex and ey. So here, if say that p point is at infinity, that d is very, very greater than L, then what you effectively see from p is a point charge, not a length L. You see a point charge. And that means if you see a point charge and on the same axis of point P, then you have Ex component 0 and you have Ey for the point charge. That is Aeq by r square. That is Coulomb's law. Okay. I hope it makes sense. So what you effectively seeing from infinity is not a length L. You're seeing a point P, a point charge. So that's why you're getting Ey as Keq by d square, just like Coulomb's law. I hope it makes sense. If you get it, just type yes. Okay. I have no idea to know whether you guys got it or not. Okay. Perfect. Thank you. Let's move on to the next question. This is the simple one. I haven't, yeah, there's no integral involved in this one. So yeah, yay. So let's go through the question. A charge is at the center of the cube. We have a cube in which the charge is at the center, and there's certain dimensions given. So no other charge is nearby. So find the flux through each face of the cube, and find the flux through the whole surface of the cube. Okay, let's first go through the part A and B. So let's say first break down. Come on. So first break down the problem into the given. What is given? A charge enclosed. It's very important too. So let me emphasize the fact the charge is completely enclosed in a closed surface. Okay, that means according to Gauss law, if a charge is enclosed in a closed surface, then the flux is given as charge, what is this? Charge enclosed divided by epsilon naught. As simple as that. Epsilon naught. Whoa. So charge enclosed by epsilon naught. Okay. What is the charge enclosed? So this is the answer for part B actually. So this is the total flux through any closed surface according to Gauss law is the charge enclosed. Charge enclosed is 170 microcoulomb 10 to the power minus 6 coulomb divided by epsilon naught is 8.85 into 10 to the power minus 12. And the unit of Gauss flux would be Newton per coulomb meter square. That's your answer for part B. For part A, by symmetry, you just phi E face. So from each face, because there are 6 faces of a cube, I'm just typing by symmetry, we get 1 by 6 of phi E total. So this is phi E total. Okay, I hope it made sense. Okay, Where is 8.85? It's a constant. It's epsilon naught. It's the value of epsilon naught. It's a permittivity of free space. So in vacuum, the value of epsilon naught is 8.85 into 10 to the power minus 12. And in the material, it changes, so you don't have to worry about that. It's not at your level when you have to worry about the relative permittivity or something. This is epsilon. This is a pretty constant value for a vacuum. Okay, so it's okay. I'll give you a little bit extra here. So you know how they figured out the Maxwell figured out the speed of light thingy is, I'll show you. 1 by c square is mu naught epsilon naught. So you know what Einstein came up is when he was doing his spatial relativity and the general theory of relativity, he was working with the equation, and these two things keep on coming, mu naught epsilon naught. I think so, you have that. Yes. Okay, well, I'll just give you epsilon naught. I'm giving you the behind story about the mu naught epsilon naught thing. So when Einstein was working with the equations, every equation, these mu naught epsilon naught keep coming. Then he calculated the value, and it was coming to be 3 into 10 to the power 8 meter per second. Then he concluded that this is the constant speed that is equals to mu naught epsilon naught, that is permittivity of this free space. Then he concluded that speed of light is constant in all the universe, doesn't matter where you are. Okay, it's a lot to it. I'm just giving you the brief of it. Okay, I don't want to be going too off topic so you guys get confused or something. Okay, if you want, I can go ahead. I love that part. Okay, so let's go to the C point. What if? Would your answer to the either part A or B change if charge were not at the center? So we have yes or no. If the charge at the center, let's vote for the part A. So those who is in the favor that yes, the answer would change of part A if the charge is displaced from the center of the cube, say yes. If somebody says no, if somebody thinks it's no, it won't change, type no. Okay, let's see. Okay, okay, everybody's no. Okay, here it is. I feel very sorry to break it for you, but for the part A, yes, it will change. So flux through each face of the cube will change, but total flux won't change. Okay, I hope it makes sense, because if you have a cube, if the point charge is here for the part C, then the field lines comes out as this. You can see the number of total electric field lines going through each surface changes if you displace the charge q. But according to Gauss law, the total flux won't change, because the total flux is just the charge enclosed by epsilon naught. Okay, so not bad. Okay, not bad. So it's just you have to see through the question. It says flux through each face of the cube, and the B says through the whole surface of the cube. Okay, so for part A, yes, it will change. In C, the answer in A will, oh, come on. So answer in A will change, but B will remain constant due to Gauss law. If we were given this part C, how would you describe in words what's happening in that picture? if we were given this part C. Okay, I didn't get the question. Okay. How would we expect it to explain this? Okay, it's the question just asks what would your answer to either part A or B would change if charge were not at the center. So initially it was given that charge is at the center of the cube. Okay, this is a square, but in 2-dimension cube looks like a square. Okay, so charge is at the center, then you displace it from the center. Any point, anywhere, you can displace it here, here, doesn't matter. And then they're just asking a conceptual question. The concept they're trying to ask is whether the flux through each surface of the cube, or you can call it each face of the cube, you have 6 faces in cube, would change or not. Yes, it will change, because what is the flux? Flux is the number of electric field lines entering or leaving the system. Okay, so yes, the number of electric field lines going through the each face will change. That's why your answer in A will change, but answer in B won't change, because Gauss law says if it's a closed surface, then the total flux through the surface is dependent not on the shape of it, it's just dependent on the charge enclosed. Is it okay, Riley? Oh, perfect. Let's go ahead to the third question. Okay, this is a very similar question. I already have drawn the figures because I'm very terrible at drawing them. Okay, a particle with charge 12 microcoulomb is placed at the center of spherical shell of radius some dimensions, 22 centimeters. So you have a charge Q. You have charge Q at the center of spherical shell. In the second part, you have charge Q. Now you have the hemisphere instead of a spherical shell. You just cut the half part of the spherical shell. Oh, yeah. So, as you encountered in the earlier problem, the answer, no, first let's look at the given part of it. That's how you deal with the questions always. Always write down the given part, okay? Given part is charge is enclosed in the spherical surface. Okay, for some of you, maybe it looks like, oh, why do we write given part? It's obvious. But believe me or not, it helps in physics if you explicitly write it in your questions, in your answers. It will help you if you read it again and again. So it says charge is enclosed here. That means you can apply Gauss law. Gauss law says in any enclosed surface, the total flux through it is charge enclosed in it, divided by epsilon naught. So I can directly figure out the answer. Flux to a sphere is charge enclosed divided by epsilon naught. You substitute the values. You substitute the values and you type 12 into 10 to the power minus 6 coulomb divided by 8.5 into 10 to the power minus 2. And the unit is Newton per coulomb meter square. What did you write 9 EM? No, it's charge enclosed. Sorry for my sloppy writing, okay? I'm better. Charge enclosed. EN is enclosed. Okay, it's subscript, not that big a script. Now you got it, Khalid? Okay. Perfect. So this is it. And for the B part, you can tell by the symmetry for the hemisphere. For the hemisphere, flux is half of sphere. So just half the value of the phi sphere. Okay. C part. Okay. Again, it is a voting question. Do the result depends on the radius? So whoever of you think yes, it depends upon the radius, say yes. Whoever you think, say no. So for B, it means that it gets half of the field lines, right? Yes, because the charge enclosed. Yes, perfect. According to Gauss law, and all of you got it correct. Perfect. As that means you're getting it. I'm happy. So Gauss law says that it doesn't matter the dimensions. Let's say this is the dimension. What matters is it should be a closed surface. Okay. Then the flux through the any weird looking surface is just the charge enclosed divided by epsilon naught. Perfect. Let's go to question number 4. Wait, but the hemisphere is closed? Yes. So you have the surface here on the bottom. It's a hemispherical shell. Yes, bottom will get half the field lines. That's why it's exactly half, according to the Gauss law. Thanks. Perfect. Let's go ahead. Question number 4. Okay. Again, we got the voting question. The closed surface, so the question says, find the net electric flux through figure A, the closed spherical surface in a uniform electric field. Okay. So what is electric flux? Electric flux is number of electric field lines coming out of the surface subtracted by the electric field lines coming in. Okay, I gave you what is electric flux. This is electric flux. Number of electric field lines coming out of the surface subtracted to the electric field lines coming in. So how many of you think in figure A that electric flux is 0? So yeah, Christina, you got it correct. So electric flux is 0 because it's a symmetrical surface and the number of electric field lines that are coming out is exactly equal to the number of electric field lines that are coming in. So you have 0 flux. Isn't anything outside always 0? What anything? I didn't get the anything part of it. If it is a closed surface, yes. Yeah, there's no Q enclosed. No, the thing is, okay, I'll tell you this. I'll make a case for that. According to Gauss law, if you have a charge enclosed, then there is no flux going out. Then the flux is this. Okay, charge enclosed. How did we determine the sphere is symmetrical? No, sphere is a sphere. Sphere is always symmetrical. You don't have to determine that. It's a symmetrical surface. All right. Yeah. Okay. Yeah. Gauss law says that if you have a charge outside any closed surface, okay, then the total flux is zero through that surface. Yes, you're correct. But the point is, it should be a closed surface. That's what the point I'm trying to make here. So for the Gauss law, it is important to define symmetrical for what in Gauss law you can only apply Gauss law in the symmetrical surfaces. If you read your book, it's a criteria to know if you can use. Yeah, exactly, Riley. So it you can apply Gauss law only in the symmetry conditions only. So when Gauss first did it, he assumed there is a Gaussian surface, and that Gaussian surface always has a symmetry. So there are 4 laws which you have to follow. You can go and read it in the book again to choose a Gaussian surface, and it's always symmetrical. So for a line charge, it has a cylindrical symmetry that you have to use polar coordinates. For a spherical symmetry, you use spherical coordinates, stuff like that. And for planar symmetry, you use Cartesian coordinates, a pillbox problem. I just wanted to make it easier, okay? So it won't work. It works for an irregular surface. No, okay, we can't apply Gauss law there. But if it's a closed surface, the total flux through it remains zero if there is no charge enclosed in it. Does that make sense? Oh, perfect. Perfect. Also, we were talking about it, so let me give you another fact. You all traveled in an elevator. You always wondered, why there is no signal. Anybody of you wondered about like why there is no signal in an elevator? So whenever you go in elevator, your mobile loses signals, right? Your cell phones doesn't have any signals. Cause of conductor? Nah. Yeah, kinda. It's not a full answer though. Faraday cage. Yeah, that's the word. Faraday cage. That's the word, Faraday cage. So what Faraday cage tells you, if you are inside a conductor, then you are shielded by any external electric field. That means this is a hollow. You're here. I'm a little off topic, so you can ignore it. But that's a fact I wanted to share. Because you're surrounded by a conductor. Perfect. Yes. So the Faraday cage is the thing. If you are inside a hollow conductor, then you are shielded by any external electromagnetic field. That means the charges are induced here and the charges are induced here accordingly, and it cancels the effective external electric field. This is why when you travel in a plane, your pilot can take your plane through the thunderous weather and the electric storm, because even if the electric field lightning struck on your plane, you are shielded by it because your plane acts as a Faraday cage. No, they don't go around it. They are not magnetic field. They go through it, but they get cancelled because it's a conductor. You have opposite charges, so you develop a field in the opposite direction. So if you ever wondered, you are in a plane and the plane is going through a lightning storm, then even if the lightning struck your plane, you're safe because it acts like a Faraday cage. It's a little fact. It has nothing to do with the question, but I thought it's a cool one to share. Okay, we can forget about it or keep it there. Okay, so let's go to the question B, the closed surface shown. So now we have a cylinder, and if you can see closely, we have electric field lines emanating from it, so coming out of both the ends. So what is flux? Flux is E dot dA and through the curved surface it is 0 because it is parallel to it. That means phi cylinder can be written as phi circular surface plus phi curved surface. Phi curved is 0 because E dot ds is E ds cos 90. That is 0. So we have phi circular phi cylinder. What does 2r represents again? Here is just the radius. So 2r is the diameter of the cylinder. Oh, do we have to always write the vector sign for A on the exam? Yes, you always have to, and sorry for my inconvenience caused. So you always have to write it, okay? Vector signs. Some physicist doesn't like it, and I don't know about your prof, but you have to write it, okay? So you always write the vector signs. So now phi circular is just E dot dA, and that will be E pi r square, area of the circular part of it, pi r square. And because we have two surfaces, then I'll keep that'll be equal to E pi r square, or equal to 2E pi r square. That's okay. So the total flux through the cylinder is 2E pi r square. Now let's go to the C. What can you conclude about the charges, if any, inside the cylindrical surface? Okay. So as you can see, because the total flux through the curved surfaces are 0, as here, total flux through the curved surfaces are 0, and the field lines are coming out of it, the cylinder, then this means that the charge inside is positive. I'll write it. C, charge inside is positive and distributed parallel to the curved surface. I hope it makes sense. How do you know the curved surface is perpendicular? Wait, where did I type it as perpendicular? Is that 2E pi r square? Yes, this is 2E pi r square. The angle 90 is so flux is 0. Okay, yeah, because as you can see, the electric field lines are parallel to the surface. That means if the area vector is like this from the curved surface, that means the angle between E and the so the electric field lines through the curved surface is perpendicular to E, as you can see here. What is the area vector? From any surface, area vector is normal to it. Yes, everywhere on the curved surface is perpendicular. Yes. Okay, perfect. Okay, let's move on to our fifth question. So, an insulating rod having linear charge density, let's write it given, as we always do. Given linear charge density, that is charge per unit length, is given as 40.0. 40.0 microcoulomb per meter. Okay. And linear mass density, mu mass per unit length, is given as 0.100 kg per meter. And electric field is given as E field is given as 100 volt per meter. Okay, so what we have given is an insulating rod with the certain charge distribution that is distributed uniformly along the length, is released from rest. So the point to be emphasized is released from rest. Okay, that's how you break the question. That's how you get your answer. You always see what is given. So it's released from rest in a uniform electric field. So everything is uniform. You don't have to worry about anything like symmetry or the charges or the angular field distribution. Everything is uniform and the charge is released from the rest. Okay, so the first question says determine the speed of the rod after it has traveled 2 meters. So A, you have to determine the speed. So whenever you see, so this is electricity and magnetism and mechanics question. So both of them are here. So if you remember your mechanics, so it says that total energy is always conserved in any system, in any closed system. That means if it's free of external forces, then the total energy is always conserved. So this system, it's released from the rest. That means it has initial potential energy plus kinetic energy should be equals to the final potential energy plus kinetic energy. Okay, you got it? And because it's released from the rest, Ki is 0, and we can assume Ui to be 0, potential energy initial. Okay, because we didn't know any the state of the system before, we have the liberty to do that. Now we have UF and KF. What is UF is QV, that is charge into voltage, that is potential, and that can be written as Q lambda L. Sorry. So it can be written as Q Ke Q by R. That can be written as Ke lambda L square by R. Okay. I hope it makes sense. If it makes sense, please say yes. What is the denominator? Pi? No, it's R. It's just formula for voltage. Yeah, we don't have any potential energy in the beginning because we don't know the state of the system, and it says it started from the rest and it's not in the electric field, so we can assume that there's no electric field in the beginning of the system, and we can say that potential energy is 0 in the beginning. because there was no electric field in the beginning. We don't know the state of the system before. So V kq by r, yes, V is kq by r. Okay, perfect. Now we can, why is the lambda I squared? Because there's 2q, q square. Oh, thank you. Oh yeah. So if you don't want to write it, you can write it like this as well. Q into E into D. You know V is also ED, right? So you can write it like this as well. And then this will be lambda L ED. That makes sense to you guys? You can write it like this as well. Yes, perfect. Perfect. Because then I had to define R. I can simply say lambda LED, where D is the distance traveled and E is the external electric field. So I save myself doing the mathematics there. I use the what is given. And what is Kf is half mv square. V is something you have to find, and m is given as mass, linear mass density, that is mu into L V square. Okay. And one thing, that potential energy that is final is negative lambda LED. And somebody can ask me, oh, not this D LED, that D small d. Somebody can ask me, okay, I didn't write D. D is 2 meters. T is 2. Where is it going? Yeah, 2 meters. D is 2 meters. Somebody can ask me why it is negative. Because the work is being done on the system to move it from point A to point B. So whenever the work is done, it is always negative. I hope it makes sense. Okay, please type yes if it makes sense. Okay, perfect. So now you can write it as 0 plus 0 equation 1. What is that? Equation 1, equation 1, autocorrect. Equation 1, you can type it as half mu LB square minus lambda LET. From here you can type, find your V as, you just rearrange the terms, you get 2 lambda E T by mu. Come on, autocorrect. So that's how you find it. This is your answer to the first part of the question. Determine the speed of the rod after which it has traveled 2 meters. You get your velocity. Okay, so the second part of the question, what if, how does your answer to part A change if the electric field is not perpendicular to the rod? So what do you guys expect? Would it change if the electric field is not perpendicular to it? Before saying yes or no, just think what we did here. We equated total energy before and after, so conservation of energy. Does it depend on any angle or of the electric field? No. Perfect. So Riley, yeah, it's correct. So it doesn't depend on if the angle of the electric field is different, if it's not perpendicular to it. It will still travel certain distance, but the equation and the formulation remain same. So each bit of rod feels the same force as before. Okay, the formulation won't change. Would it still move in the same direction? No, it will always move in the direction of electric field. Okay, so the force due to electric field, this is a slight detour, not B part. Force due to electric field, force is a vector quantity, is QE. Okay, my writing, please excuse me. So QE. So you see force is in certain direction of the electric field. That means it's always in the direction of E. Does that address your query? That makes sense. Okay. Let's move on to our sixth question. Very easy one indeed. So here we have given 2-point charges, Q1 and Q2 are separated by 35 centimeters. As you can see, my little drawing, it says that there are 2 charges plus 5 nanocoulomb and minus 3 nanocoulomb separated by 35.0 centimeters. Now, first part, let's say given 2-point charges, 2-point charges separated by certain distance. So what do we infer from the given is that this is not a continuous. It does not matter which charge you put on which size. No, it doesn't matter at all. This is okay. So I'll tell you, in the question we always assume this is a free system. That means it is free of external forces and there are no charges around. There are nothing around. So we consider this as a free system, free from external forces. All the questions in physics. So when you do real world problem, you consider these things. Okay. In the end, towards the end of the session, I'll tell you how do we do that in research. How do we consider it, but not right now. Okay. I think it's a cool fact to point anyway. So given 2-point charges separated by green certain distance. So what do we infer from given here? That this is not a continuous charge distribution. This is certain 2-point charges are separated. Okay. So that means in order to find the electric potential at a point P that is exactly midway, you have to use the discrete charge formula. Does it make sense? That's what we infer from the given. That I don't have to use integrals, I have to use discrete charge formula. Okay, I hope it makes sense. Wait, somebody's typing. I'll wait for them. What does the first part of the equation say? First part of the equation? This is a summation sign. This, okay, I'll make it better. This is the summation sign. Summation over all the charges. Wait, it is this because they are point charges. Yes, because they are discrete. They are not continuous. That's what we get from the given part of this question. That's what I'm trying to emphasize, that in all the questions in physics, you see the given part and then you infer what do you want, what do you require. If I had applied this formula like this, voltage KE dq by R, then it wouldn't have made any sense because it's not a continuous. I can't apply an integral. Are point charges always discrete? Yes, if they are given in discrete way. If the point charges is distributed uniformly across a length or across any surface, then it's a continuous charge distribution. Okay, so my aim here is not to teach you just the solutions or just to give you the solution of certain challenge problems of your book. My aim here is to train you to tackle the problems of physics, because if you just want the solution, you can go look at the solution manual as well. It won't make any difference between me and the solution manual. Okay, I just my aim, I just want to clarify, my aim is to just train you to tackle the problems of physics. Okay, let's go ahead. So you apply this. Now what you get is just you take q outside plus 5 into 10 to the power minus 9, 0.175 meters minus 3 into 10 to the power minus 9, 0.175. That's your answer to the first part. So what is the potential energy of the pair of charges for the second part? And what is the significance of the algebraic sign? Okay. So let's see. First let's see what is potential energy is U equals to QV. Okay. What is your Q? So it is KE Q1 Q2 by R. So what is KE? Q1 is plus 5 into minus 3 into 10 to the power minus 18 Coulomb by R. R is 0.175. Oh, sorry, is the pair? It's a pair. It's not that the potential energy of pair of charges. That means 0.35. Okay, and so it is negative. I told you what is the meaning of negative energy. That means the work must be done in order to separate them. Okay, because this is a positive charge, this is a negative charge, they will attract each other, and the potential energy is negative. That means external work must be done in order to separate them. Make sense? Perfect. That's your question number 6. And question number 7. That's the last question of the day. I hope I'm not over time. Let me look at the time. No, 10 minutes. Okay. So what we have given here, a wire with a uniform charge density L, lambda. So given, again, uniform linear charge density L, lambda, come on, lambda. So, and somebody were not having a good day, they bent this uniform length of wire into this kind of shape. Okay, I don't know why that guy did that, but they made our life difficult. Okay, let's make it easy now. They did that. They really hated us, and they wanted us to solve this question instead of a linear length. No, but we are smart. We can tackle it. Okay, we have to find the potential. So first of all, this is potential due to a continuous charge distribution. All of you agree with this. Okay. Now we can give this as origin and these things as coordinates. Smartly so. Make sense? Where is V? Oh, potential. Oh my god. Okay. This is the formula for potential. I don't know, this is the same symbol for V and velocity and some potential, but this is potential. Okay. Okay, so we have this is the formula for potential. So we have, that's what we have to find, electric potential at point O. So we have to find electric potential at point O. Let's call it our origin, okay? And we have to find the electric potential due to this shape at point this. So we divided this into coordinates. We gave the coordinates as r, 3r, minus 3r. Now we have to just distribute the integral. Make the continuous integral like this. Okay, I'll write it. First of all, minus 3r to r lambda dx by minus x plus ke lambda dx, sorry, lambda ds by r. Why I'm writing here s, because this is surface area of semicircle. Plus, because it's a symmetrical shape, I don't have to do anything else. Okay, so this is the equation. Let's see if it makes sense or not. Please type yes if it makes sense. Oh, I just divided the line from minus 3r to r, then an area of semicircle, and then r to r. Okay, how can I figure out the upper and lower limit of the integral minus 3r to r? So okay, so I just divided here. This is how I figured it out. So because it's given 2r, I can write minus r to minus 3r. Those three represent the three sections. Yes. Do we have to have the bounds on each one or only on the first one? None, on each one. And the middle one, the one with the semicircle, is already has a symmetry, so we can find the total area or the curved surface area or perimeter. Okay, half perimeter of semicircle, something like that. Are the bounds on the middle one are no? You don't have to write it r to minus. It's a bent shape. It's in the shape of semicircle. Okay, so the total length of the semicircle you already know is pi r. So you don't have to do the integral over there. You just write ds. That's smart way to do that. Otherwise, you have to find the angles and then the projection into the Cartesian coordinates, and then you have to do integral over that. But you don't have to go through it. Somebody already did the hard job of finding the perimeter of circle. That is pi r. Semicircle. That is pi r. I hope that makes sense. Okay, perfect. And none of you asked me why there is a minus x. Can anybody explain to me why there is a minus x? Yes, perfect, Willie. So this is the negative direction because I consider this as O, then I consider this as minus x. So because I have my reference point is this O, if my reference point had been here, then I would have given it as 0 to 2R, then 2R to 4R, and 4R to 6R. Then this would have changed. Does that make sense? Yeah, makes sense. Okay, so what is this integral? This is our favorite logarithmic x. Now all you have to do is apply limits and solve the question. So do you want me to solve it further, or are you just applying the limits? Please solve further. Okay. I'm here for you. Okay. So there's this property of log a minus log b, not log, natural log, and b is, I hope you guys know that. So this will be ke lambda in the line above. Should it be ln of minus xs or ln of x? Okay, wait. So that's your answer. Okay, where are you asking, Christina? You have negative here, that's why you have negative in front. Sorry, why did I make a mistake? Wait. I think I made mistake somewhere with the second highlight. Wait, yeah. I think I made mistakes on some typos here. So 1 of r minus 3r. Oh yeah, there shouldn't be this negative there. But it doesn't make any difference. Yeah, it should be ln of x. But it won't make any difference even if you put minus. Oh, come on. If you put minus here and here, it won't make any difference. Because it will go in divide a by b, then it will subtract it. It will cancel out. Oh, that was a typo. Thank you very much. Thank you for correction. Okay, so let me conclude today's session. So in today's session, we learned about Gauss law. We learned about potentials. Okay, and we looked at certain continuous charge distribution problems, Gauss law problems, and potential. And most importantly, we learned that in every physics problem, we always start with the given and then we try to infer the physics out of it. And another thing I would like to conclude is that you should always emphasize on getting the physics right. Don't fear with the mathematics. Don't fear with the mathematics. Even if you get the mathematics wrong, if you get the physics right, you still get half the marks in physics. Okay. Thank you very much for attending the session. It was a great session. I enjoyed it. I hope you liked it. I will post the, as I said before, I have recorded this session. I will post it on Facebook, or if I want to make a YouTube channel, I can make a YouTube channel as well. I'll post the recording there as well, so you guys can go ahead and hear what I was saying. It made sense at some point. So I'll post on Brightspace as well. Yes, I'll post the PDF on Brightspace as I did for the last lecture. I'm really sorry. Can you move the next one? Yeah. You don't have to be sorry. So I'll post the lecture on Brightspace. And thanks a lot. Have a wonderful weekend ahead. See you next time. If you have any query, you can say it to me right now. Wait, you have a query. Let me see. Because you have negative KE in front. Oh, another typo. Thank you, Christina. Thanks a lot. This should be positive. This should be positive. Yes, you're right. This should be positive. Yeah, this should be positive. Yes. Perfect. Thank you very much. Thank you, everyone.